Welcome to The Deep Dive, the show where we cut through the noise and get straight to the insights. Now, if you've ever felt just completely overwhelmed by the sheer volume of information out there, especially the kind artificial intelligence models are trying to make sense of, well then today's deep dive is definitely for you. AI is trained on these huge mountains of data, right? But how do we move it beyond just being a vast, sort of unstructured web of information? How do we make it truly intelligent, precise, and maybe most importantly, reliable? That's really the core challenge we're unpacking today. Our mission is to explore how we organize all this knowledge, specifically using something called an ontology model. And we're going to dive into how tables, those familiar grids of rows and columns we all know, are becoming this critical tool and building a more structured, more accurate future for AI. We're drawing our insights from some fascinating lecture notes. They're titled Table Maker Ontology Modeling for Tabular Representation. They're by Jae-Hwa Choi, who's an associate professor at George Washington University and also the principal investigator of the CAFA initiative.
That's CAFA, pronounced like CAPA. Okay, let's unpack this.
Yeah, it's fascinating stuff. And what's really striking here is how something, well, seemingly as basic as a table can become so foundational for these really complex AI systems. So just to kick us off, an ontology model. Think of it as a formal, explicit map of knowledge within a specific area, like a really detailed blueprint. It defines concepts, lays out their properties, and crucially shows the relationships between them. And this isn't just about being tidy, it's about moving AI from making broad guesses to real precision. Imagine an AI going from just sort of guessing an answer to making a logically verifiable decision. That's the kind of leap an ontology model allows. It turns that fuzzy understanding into clear logic and really boosts accuracy. Now, there are different ways you can represent these models. You might see hierarchical ones like trees, good for parent-child stuff, or maybe topological ones like DAGs, directed acyclic graphs, which are more flexible for complex relationships. But today, like you said, we're really focusing in on the maybe surprising power of tabular representation.
That's a great setup because, when I first hear ontology model, my mind goes to complex diagrams, maybe abstract charts. But then you say tabular representation, and bam, it's a table, like a spreadsheet. So for anyone listening who might be thinking, a table, really? How is that revolutionary for AI? Can you break down what it actually is and, maybe more importantly, why something that feels so simple becomes such a powerhouse?
It's a brilliant question, because that simplicity is precisely its genius. Tabular representation is just that. Information organized into a structured grid, rows and columns. It's a format we all just get instinctively, whether it's a spreadsheet, a database table, even a simple chart in a report. It's real power. It makes complex info instantly comparable, analyzable. You can spot patterns or missing pieces almost at a glance.
Right, so we're essentially talking about taking maybe messy, scattered information and forcing it into that grid format we all recognize. Like my grocery list, but way more complex. What's the kind of hidden power in that simplicity? Because anyone who's tried pulling quick insights from like a dense paragraph knows how elegant a table feels.
Exactly. And to make it even more intuitive, think of it like a super well-organized filing cabinet. That analogy really works. So in this picture, the rows in our table, those are like the individual file folders. Each one holds info on a single thing, a person, a product, an event, whatever it is. Okay, then the columns are like the labeled dividers inside each folder. These are the attributes, the features of those things in the rows. So for a person folder, you might have dividers for age, city, job. For a product, maybe price, color, SCO, CIFU. Every column holds the same type of information for every single row, for every folder, consistent. And that header row, the very first row at the top, that's just the labels on those dividers. It tells you exactly what's in each column. It's this immediate clarity, this structure that unlocks the power for analysis.
I really like that filing cabinet analogy. It makes it so concrete. So, okay, it makes sense to us humans. But how does this structure, these tables, also function as a kind of universal language, connecting humans and machines in knowledge engineering? That sounds like a pretty big claim.
It is a big claim, absolutely, but it really does hold up because tables serve both sides, human and machine, incredibly well. For us, for humans, they're just so much easier to prepare and read. They cut down the cognitive load massively compared to wading through text. You scan a table, find what you need, grasp relationships quickly. If you see an empty cell in a comparison table, boom, missing info. Obvious. That clarity gets lost in paragraphs sometimes. So for human experts validating data or just exploring it, tables are fantastic.
Okay, so that visual clarity, ease of use for people makes total sense. But is it always that simple for machines? I mean, isn't getting raw, messy, real-world data into these neat tables a huge challenge? Because that's where the AI actually has to work with it, right?
That's a really crucial point. And yes, data preparation, getting it into the table, that can definitely be the hard part, the cleaning, the structuring. But once the data is in that tabular format, that's where the magic happens for machines. Tables are basically the default, the standard input for tons of algorithms and data analysis, machine learning, you name it. That structure lets a machine process information super efficiently. It can sort by any column, filter for specific values, run calculations easily. Think about calculating an average price across thousands of products, or finding all records matching a specific criterion. Trivial for a machine with a table. Almost impossible with unstructured text. So yeah, getting it in can be work, but the payoff for machine utility is enormous. Tables really do bridge that gap between our intuition and the machine's efficiency. They're a cornerstone of this idea of evaluative knowledge engineering, where humans and AI collaborate effectively on structured data.
That's incredible for data we already have. But what about AI creating new structured knowledge? I've heard large language models, LLMs, are doing some amazing things lately, but can they actually generate these kinds of sophisticated analytical tables themselves? Like pull structured insights out of their own vast knowledge? That seems like a huge leap.
Oh, it absolutely is a game changer. And yeah, this is where the story gets really exciting. LLMs aren't just, writing poems or code snippets anymore. You can prompt them to generate different kinds of analytical tables, structuring information in some really quite sophisticated ways.
Okay, wait, so we're teaching AI to love spreadsheets now. Is that what's happening? It's quite a thought. What kinds of tables are we talking about? Can you give us some examples of what an LLM can actually create?
Sure. So probably the most common type you'll see, and it's incredibly useful, is the comparison table. This just organizes information by listing, say, different items in the columns and the features you're comparing in the rows, or vice versa. It's great for just quickly highlighting similarities and differences. And what's really powerful here is that when you prompt an LLM to make one, it's effectively doing a kind of automated feature engineering. It has to figure out the relevant things to compare. Like, you could ask it, provide a table comparing moth and butterfly. It would likely identify criteria like antenna, pupation, activity time, and lay out the differences clearly. Then you've got the contingency table. You might know it as cross-tabulation. This one's really good for showing frequency or relationships between two or more categorical variables. You might have categories of one thing in rows, another in columns, and the cells show how often they occur together. Like, you could provide a contingency table between animals, rows, and habitats columns. The LM would try to populate that, showing perhaps which animals tend to live in which habitats based on its knowledge. It's a fast way to visualize those co-occurrences. And one more, which is really clever for knowledge domains, the hierarchical table. This is a neat way to represent tree-like structures, hierarchies, in a flat 2D table. It sort of flattens nested information. Each column might represent a deeper level in the hierarchy, makes complex layers easier to see. You could ask, outline the components of medical imaging in a hierarchical table, and it might list, say, radiography, MRI, ultrasound at one level, then break down their subtypes or principles in the next column. Turns a complex mental map into something clear and linear.
Wow. Okay, that is amazing. It's one thing for an LLM to just answer a question, right?
Yeah.
Or write a story, but to actually structure complex information into these useful analytical formats, that feels like a whole different level of intelligence is happening there. What's going on under the hood when an LLM does this? What does it tell us about how these models are maybe thinking about knowledge?
Yeah, it's definitely more than just a neat trick. It feels pretty fundamental. What's happening when an LLM generates a table? It's not just formatting text, it's doing something much deeper. It's performing a kind of sophisticated, automated feature abstraction and relationship analysis. Think about it. The AI is essentially learning to organize its own knowledge, transforming its vast but often implicit understanding into something explicit and structured. It's almost like it's building its own internal spreadsheet of how the world works, based on our prompts.
Organizing its own knowledge. That's a powerful way to put it. So it's taking all that unstructured stuff it learned and formalizing it.
Precisely. An LLM's knowledge is usually implicit, tangled up. When we ask for a table comparing A and B, we force it to make that knowledge explicit and structured. It has to pick out the key features like the antenna for moths and butterflies. It has to define them in a way. So the table it produces, it's not just data display. It's a newly formed knowledge model, turning fuzzy understanding into something concrete. And second, think about that contingency table example. When it fills in those cells showing animal habitats, it's not just putting numbers there randomly. It's actively defining and quantifying, based on its training, the relationships between those categories. A simple prompt makes it analyze complex interactions and summarize them structurally. And maybe the biggest implication here, this whole process turns unstructured concepts into a format machines love, that generated table. It becomes a valuable knowledge asset. Humans can check it, expand it, and critically use it as direct input for other AI tasks. This lines up really well with this idea of omega ontology model emulation by generative AI. The whole point is using AI to help build these structured, usable knowledge representations. But this does raise a big question, doesn't it? How do we harness this reliably? LLMs can sometimes, well, hallucinate. How do we make sure these AI-generated tables are accurate and not just beautifully structured nonsense?
Exactly. That was my next thought. This seems incredibly powerful, but also potentially risky if the AI gets it wrong. So this must be where the practical application comes in. Creating the table with the LLM isn't the end goal, is it? It sounds like just the start of a workflow for creating and using properly validated ontology models, like a partnership.
Yeah, maybe you can walk us through that. What are the steps in this Omega workflow you mentioned? First, I assume, is the AI-powered table generation. The LLM makes first draft.
That's right. Step one, the LLM drafts the table. It acts as that initial knowledge extractor, pulling out key features and relationships from its data, provides that starting point. It does the initial heavy lifting of organizing.
Okay, saves a lot of human effort up front, but like we said, it needs checking, so what's next? Step 2, export and human review. Critical step. The table the LLM generated, maybe it's in Markdown or just text array, you can easily copy that into a standard spreadsheet, Google Sheets, Excel, whatever. And this is where the essential human-in-the-loop part happens. A domain expert, someone who really knows the subject, reviews it. They edit, confirm, validate, check for accuracy, completeness, make sure it makes sense in context. This human validation is absolutely key to ensuring quality and catching any AI errors or weirdness.
Right, the expert sanity check. Makes sense. So once the human expert blesses the table.
Then step 3, import and utilize. That validated table now becomes a trusted ontology model. It's formalized knowledge, and it can be accessed by, say, a CAFA agent using specific commands. The notes mention things like @gs, or maybe more directly, @gstable, @glued clue. This lets the agent pull that clean, structured, expert-verified data right from the spreadsheet, maybe even in real time. It makes the knowledge immediately actionable.
Okay, so the validated knowledge is now accessible to the AI. And the final step.
Step 4. Ontology-centered content service generation. Now, with this high-quality, human-vetted knowledge base ready to go, the AI agent can perform its downstream tasks much more reliably. Whether that's generating new content based on that knowledge, answering complex questions accurately, or providing some kind of service. The AI isn't just relying on its own potentially flawed internal knowledge anymore. It's using a structured, accurate, expert-approved model of that domain. So this whole cycle, AI generates, human validates, AI utilizes the validated version. That's a really practical example of the Omega framework in action. It really does feel like a true partnership between human smarts and AI power. So just to wrap up our deep dive here, tabular representation, it's clearly way more than just a simple grid. It's really a powerful kind of universal tool for structuring knowledge. It bridges that gap, doesn't it, between how we humans grasp information intuitively and how machines need it structured for processing. And this ability we're seeing to use AI to help turn implicit, messy knowledge into explicit machine-ready formats, that's genuinely transformative. It enables more advanced AI, sure, but it also fosters this really crucial collaboration between people and machines. In this age of just information overload and ever smarter AI, the value of having validated structured knowledge, you really can't overstate it. It's foundational.
Absolutely. So what does this all mean for you listening right now? Just think about how many unstructured documents you have, or notes, or even just ideas scattered around. Could turning some of that into a simple table, maybe even getting a little help from an AI to draft it first, could that unlock totally new insights for you? Could it make your own knowledge more powerful, more accessible, more usable? We invite you to consider how sometimes the simplest structures, like a humble table, can lead to the most profound understanding, and how maybe, just maybe, getting organized with a table could be the key to your next big aha moment.